All right. So, like I said, we're doing something a little bit different here. Nothing to do with Einstein, specifically, anyways. And that's called the photoelectric effect. Now, here's what and this is relatively new in physics, which means last 30 years. That's kind of new. And what the photoelectric effect is all about, it's a phenomenon, and they don't know all the details about this, but it is the phenomenon of electrons being ejected from a metal when exposed to electromagnetic radiation. All right, so we're going to talk about electromagnetic radiation here shortly. But a word I'm going to use is photon. Now, this is where the photo part of electric effect comes into play. It's not about a photograph, but about a photon. And a photon is described as a discrete bundle of energy carried by light. All right, so light essentially is carrying these photons and they have energy. The thing is that they have energy, but they have no mass and are unlike any other particle. And again, this because this is a newer topic in science and in physics, the details aren't really hammered out. They're just defining a photon, again, as a discrete bundle of energy carried by light. Now, electromagnetic radiation, on the other hand, that's nothing new. And here's the spectrum of all the different types of electromagnetic radiation. So we have like TV, AM radio waves, microwaves, infrared rays, and then there in this tiny little sliver here is visible light. Then after it is ultraviolet light. We have X-rays, we have gamma rays. Now, the key here is that with electromagnetic radiation, you see visible light here in there, but in fact, all of these types of electromagnetic radiation all have a velocity of c, which again is the speed of light. So that's 3 times 10 to the power of 8 meters per second. All right, so they all have that velocity. Now, we're going to talk about energy that is involved with different types of electromagnetic radiation. And in the end, when you look at this table here, is that high energy means high frequency. And that's what distinguishes different types of electromagnetic radiation from each other. Or frequency, again, is also dependent on wavelength. So as the frequency increases, the wavelength decreases. And so when you look at visible light and anything left of it, it doesn't hurt us. So when we microwave our food, it doesn't destroy our food. It just heats up the particles. Infrared light doesn't bother us. Radio waves, clearly, and TV waves, when those happened, they don't hurt us. But then we look at some of the high frequency rays out there, like gamma rays, X-rays, even ultraviolet rays are harmful to us if we have a lot of it. And again, that is just after visible light. But again, that's what can give us cancer, with skin cancer and stuff like that. So, and X-rays definitely even more types of cancers. So again, the higher the frequency, when we're right of visible light here, means higher energy and dangerous. Now, and I'm going to refer to light a lot because I know most of you, well, have experience with light, I hope. You see the light of day. Is that if you increase, here's some notes about electromagnetic radiation, is that if you increase the intensity, then what you're doing is you're increasing the number of photons. All right, so you increase the number of photons. So what that means is, say for visible light, if you increase the intensity, you turn the light up, it gets brighter. It means you have more photons. But see, visible light here, even though it might be brighter, it's still the same frequency. It's still times 10 to the power of 15 kind of frequency. All right, so just making it brighter just means you have more photons, but the frequency is different. Is still the same. Now, if we increase the frequency, that means you're changing what type of electromagnetic radiation you're dealing with. Well, then you're increasing the energy of each single photon. So the idea here is, say with visible light, is that if you increase the intensity, the light just gets brighter. But if you increase the frequency, you're no longer have visible light. You're now into ultraviolet light or X-rays or gamma rays. So you're changing the electromagnetic radiation. All right, now on that note, we get to what's called the threshold frequency, F naught. That's what little zero there means. And that is the minimum frequency at which electrons are ejected from the metal. All right, so again, the whole photoelectric effect is that if you shine, it says light. This should really say electromagnetic radiation, because we can have any type of radiation, not just light. But if you shine electromagnetic radiation on a metal and it's past the threshold frequency for that metal, an electron shoots out. So again, what happens is if you can shine electromagnetic radiation on a metal, but if it's not the right frequency or if it's not high enough, no electrons get ejected. But as soon as you hit what's called the threshold frequency, the electron pops out. All right. Now, the minimum energy required to remove a single electron from a piece of metal is what's called the work function. Now, we have a formula for the work function. And again, this is energy. And so we have work is equal to H times F naught. Now, again, this is where, as I mentioned up above here, F naught is what's called our threshold frequency. All right, so that's the type of electromagnetic radiation that you need to have for this photoelectric effect to happen. So again, that's F naught. Again, that is our threshold frequency. All right, now H, lucky for us, is a constant. It is 6.63 times 10 to the power of negative 34. The units, I don't worry about the units, but they're joules, joule seconds. And this is what's called Planck's constant, named after the gentleman who found this effect or phenomenon. So that's Planck's constant. So that always stays the same. But the threshold frequency for a different metal, each metal has a different threshold frequency. So again, that F naught here depends on the metal we're talking about. And that's the amount of energy that you need to have the photoelectric effect. Because if you don't have that frequency, it's not going to happen until you hit it. All right, now, the second part, again, we talk about these photons, right? That's essentially, you can look at light has energy, and light's composed of photons. Now, the energy that's in the photon is defined as H times F. So whatever frequency you do have from the electromagnetic radiation, it's H times F, that Planck's constant times F. So again, F in this case, not F naught, but just F, is the frequency of the electromagnetic radiation that you're talking about. All right, and again, F or H is Planck's constant, which, well, I'll write it down. We're going to need it again here. So when we start doing some calculations, which again is 6.63 times 10 to the power of negative 34. All right, now. And what happens is that each electromagnetic radiation shoots and has a certain amount of energy. Now, if you get past the threshold frequency and you get past the work function, which this H times FO is, that's the work value, well, then there's leftover energy. And that leftover energy goes into making the electron move, the electron that's being shot out from the metal. So again, this is the, piece it off here, where this is the energy required to remove the electron. So you need that much energy first off. And again, that depends on the frequency of the metal you're dealing with. And then this HF that you have is just the initial energy that you have, or the, I guess the initial energy of the photon that's hitting the metal. And then again, our kinetic energy after, that's the leftover energy, because the H times FO is the energy required to just remove the electron. Then the leftover energy goes into moving the electron. And then, of course, our kinetic energy here that we have is our energy left over used to move the electron. All right, so we have the energy that we started with minus the energy it takes to remove the electron, and whatever's left over is now kinetic energy. All right, now here we go. So let's get into using some equations here. So the work function for a particular piece of metal is 3.5 eV. That's electron volts. So we're going to be dealing with those. All right, determine the minimum photon frequency that can just eject an electron from the metal. So what are we trying to find here? The minimum photon frequency. That is our threshold frequency, RF naught. That's what we're looking for here, all right? So we're looking for what frequency do we need here. Now, our work function, I'm going to go down here, that we have is that this particular metal needs 3.5 electron volts. Now, that is no good to us in our formula because they're not standard units. We got to convert this into joules. Now, in the last lesson that we did here, we worked from joules to electron volts, and then actually to mega electron volts, where we were dividing by 1.6 times 10 to the negative 19. Now, because we're going the other way, we're going to multiply. So I'm going to take this, 3.5, and I'm going to times it by 1.6 times 10 to the negative 19. So I'm just working the opposite way. I'm going from electron volts back to joules. And that is going to equal, let me see here, grab a calculator. And I end up with 5.6 times 10 to the power of negative 19 joules. So that is how much energy is required to remove an electron from this piece of metal. So what would the frequency have to be? Well, this is where I'm going to use my formula here that we had initially, that the work function, the work function again is what energy is required to remove an electron from this type of metal. Now it's H, which is our constant, times FO. All right, now the amount of energy, I just converted it to joules here, is 5.6 times 10 to the power of negative 19. And that is going to equal Planck's constant, H, which again is always the same value here, 6.63 times 10 to the power of negative 34. And then, of course, what we're trying to find here is our F naught. All right, our threshold frequency. Well, all I'm going to do here is divide by that constant, 6.63 times 10 to the negative 34. And do that to both sides here. So I have 6.63 times 10 to the negative 34. All right, so those divide each other out. And so my F naught, my threshold frequency, let's see here, I divide those two up. And let's see here, what am I getting? 5.6 times 10 to the negative 19 divided by 6 point, I'm getting 8.45 times 10 to the power of 14. And again, because we're talking about frequency, this hopefully is not surprisingly to you from grade 11 physics, but frequency we might measure in hertz. All right, now That is 8.45 times 10 to the power of 14 hertz. Now, if I go back to my original table here, see we have 10 to the power of 12, and we have 10 to the power of 15 just by here. So 10 to the power of 14, it's just right in here by visible light, but I can tell you for a fact what that light is this is actually ultraviolet light. Oops. So in this case, violet, oh, jeepers. Almost, how's my spelling today? There we go. Violet, yeah, I spelled it right. Ultraviolet, I know why, light. All right, so on that scale, if you were to use radio waves, which are a much smaller frequency, and you shined it on this metal, no electron would leave. If you shine visible light on this metal, no electron would leave. But if you shine ultraviolet light, electrons would leave. And if you look at our table again, this is where our ultraviolet light is right in here. If you were to shine X-rays on this metal, X-rays have a much higher frequency, much higher energy. Not only would an electron leave, but because it's such high energy, it would leave very quickly because there would be leftover energy that would go into being our kinetic energy. All right, so that's just kind of how it works. Let's see here. We got another example here. Copper, so there's a metal, is being used in a photoelectric experiment. The work function of copper is 5.1 electron volts. Now, violet light of wavelength 425 nanometers, we'll get to what that's all about, is used in the experiment. Determine if any electrons are emitted, and if they are, determine their maximum kinetic energy. All right, so first off, we are going to look at, let's see here, copper. What copper's bringing to the table here. All right, so copper has a work function of 5.1 electron volts. Now again, that's no good to me. I got to convert that to joules. So I'm going to take my 5.1 and I'm going to times it by my 1.6 times 10 to the power of negative 19. All right, so that'll tell me how much energy I'm going to need for an electron to be removed from copper. Well, let's see here. So I take my 5.1, I times 1.6 times 10 to the negative 19, and I end up with, let's see here, 8.16 times 10 to the power of negative 19 joules of energy. All right, so this represents energy required to remove an electron from copper. Now, we've got violet light. That's what's being used here. Oh, I should use violet for violet. All right, so here's our violet light. What we're going to look at is the energy supplied by violet light because it's electromagnetic radiation. All right, so what we're going to look at here is we're going to look at the energy, which is our H times the frequency of violet light. So this will represent, again, the energy supplied or contained, I should say, in the photons of violet light by violet light. All right, so here's the problem now with violet light is I know the H value, it's always that constant, but I don't know the frequency of violet light. But here's what I do know. I know the wavelength. And the wavelength is equal to 425 nanometers. Now that means in standard units, 425 times 10 to the power of negative 9. Now, to figure out how much energy is contained by violet light, I need the frequency. Well, again, this goes back to grade 11 physics, where the universal wave equation is V is equal to F lambda. It should be on the front of your textbook, I believe, or it was in front of the old textbook. Now, here is the thing with lambda is I know the wavelength of this light and I know the velocity. Because light is electromagnetic radiation, it travels at the speed of light. All right, so I can find the frequency. So again, to find the frequency, I got 3 times 10 to the power of 8. There is the speed of our violet light. The frequency I'm trying to figure out here. The wavelength is 425 times 10 to the power of -9 nanometers. Got to convert it to meters here. All right, and then so what I'm going to do here, well, just divide. So I'm going to divide both sides here with this 425 times 10 to the -9. All right, do that on both sides. 425 times 10 to the -9. All right, now I'm going to find my frequency is, well, I take these two numbers and divide them. And the frequency I'm getting for this particular light is, let me see here, we get F equals, so I'm going to write it in here, it's a little bit easier, 7, 2 decimal places here, 0.06 times 10 to the power 14. All right, hertz. Again, that's the frequency. Now, I messed up here a little bit. This shouldn't be the work function. This is actually, as I mentioned, the energy that's contained by this violet light. All right, so now I can find the energy supplied by that violet light and see if it's enough. That's what I'm trying to do here. This is how much energy I need, this 8.16 times 10 to the -19 joules. That's how much energy I need to remove electron. And now I'm going to see how much energy I actually have because I know F of this violet light. So here we go. So E, the energy contained by this violet light, is equal to the frequency. Well, I got to do the Planck's constant first, which is 6.63 times 10 to the power of -34. All right, we found the frequency of violet light is 7.06 times 10 to the power of 14. All right, now when I multiply those two, because I'm using standard units, I'm going to get joules. And let's see here, I multiply those two. What do I get here? Okay, 2 decimal places, I get 4.68 times 10 to the power of -19 joules. And so what I'm going to do now is I compare, this is how much energy I need, this is how much energy the light supplies, and let's see, they have the same exponent here, times 10 to the -18, so 4.68, this energy is less than W, and so in this case, not enough energy there. Not enough, the frequency isn't high enough. And so, well, therefore, it's close, but no electrons are emitted. Not high enough frequency. So maybe ultraviolet light would work. Maybe it would take gamma rays or X-rays. All right, now B. What if the violet light is increased by brightness by a factor of 10? Would any electrons be admitted? So we turn up the light, we make it brighter. Well, here's the thing. That doesn't matter. No. Only an increase in frequency can force electrons to be emitted. So like I said, violet light isn't going to do it for copper. Maybe it'd work on some other metal with a lower work function, but in terms of copper, it's not going to work. So brightness only increases the amount of photons, but it does not increase how much energy each photon has. And so to do that, you have to increase the frequency. So in this case, if we got violet light in here somewhere in this tiny little sliver, well, we have to go to the right here on our scale. And so maybe ultraviolet light would work, maybe even because we were so close, maybe a different light, maybe red light or blue light. I'm not sure which one of those is on one end of the spectrum. I can't remember now. I think it's blue. But that's what it would take to emit an electron from copper. So again, this is new stuff that is new physics. Again, last 30